In this video we are going to talk about the center of mass of a hollow cone. Okay, the cone that I am going to talk about is a hollow right circular cone. What is right circular cone? Here you can see the apex directly on the top of the base of this cone, right? And this is a hollow cone, that means the mass is uniformly distributed over the surface, right? And let's say the mass is capital M here divided by the unit area is constant, that is sigma, the mass per unit area. Now the area is pi r L, where L is the slant height, right? What is slant height? The slant height is this L, okay, this length. Now what is going to be this length? Obviously you can see from here the length is square root of r square plus h square if you use the Pythagoras theorem. Okay, so now how will I find the center of mass of this hollow cone, right? So here what I am going to do, see, I am not assuming that there is a mass at base as well, right? So there is no mass at the base. Okay, even if it is there, it doesn't matter, but let's assume it is not there. Now what I am going to do is I am going to assume this circular cone, right circular cone, to be made up of many rings of varying diameters stacked over each other, right? Now this is varying diameters, and at eventually at the top you will get a smaller circles, right? Okay, so now what I am going to do is I am going to take a ring over here like this. Okay, this is a ring like this. Okay, this is the ring, and let's say we can see that, let's say the radius of this ring is small r. Let me use white color. This radius of the ring is smaller, and let's say this height over here is y. Okay, the height here is y. Okay, now you can see, let's call this point as maybe C here. Let's call this point as C and this point as D. Okay, now what I am going to do is I am going to find out the center of a mass of this small ring. Okay, this is a very small thickness ring. Now this ring, if I draw it over here, it will look something like this, with a slant height like this, and it is like this. So now this ring has a circumference of 2 pi into small r, right? 2 pi into small r is the circumference, and if I multiply with this length, let's call this length over here as dl, right? So this is not vertical length but rather a slant length. So if I write it as 2 pi r into dl, then this will be a small area of that ring dA, right? So on this we have to integrate. So okay, we will see that. Now the center of mass is of course here, and we have many such rings like this. Okay, and this cone is made up of many such rings, and we have to add the center of masses, or we have to find out the center of masses of all the rings, right? Okay, so now what I am going to do is that, see, this ring is at a distance y from the apex A. So what I am going to do, we know YCOM formula is equal to integral y dm divided by integral dm, right? Okay, now dm can be written as, see, dm integral will be capital M, that is obvious, and you have integral y dm. But now we know that sigma is the mass per unit area, so it is going to be dm by dA as well, right? So this is mass per unit area, which is constant, m by pi rl, right? So now we have here dm by dA, and from here I can write sigma into dA is equal to dm. Sigma into dA is equal to dm. Sigma times dA is equal to dm, and as I can see here, so I can write this as 1 upon m integral y into sigma times dA. So instead of dm I am writing sigma times dA, but sigma is a constant, I can take it out, and we will have integral y dA, right? Okay, but dA is nothing but 2 pi r dl. So sigma by m can be written as integral y r y into 2 pi r dl, right? So sigma is, yeah, so sigma is outside, so dA can be written as 2 pi r into dl. So let me write it properly over here. It will be 2 pi r into dl, correct? So this is the integral. So let me write it over here now. So this YCOM is equal to sigma by capital M integral y into 2 pi. So 2 pi can be taken outside of this, and we have r into y dl. So now this integral dl is over slant height, right? So my integration will be from 0 to capital L, because I am going to take my first ring over here, second ring over here, here, and so on till this end. So that integral limits will be from 0 to L, of course. But now the thing is, I have to integrate over ry. I have to find out the integral of ry as well. But how will I find it? See, r will depend as I go from here to here. R is increasing, of course. Y is also increasing, correct? So I don't know how y and r both vary as a function of L. So I have to do something about it, right? I have to write them in terms of the slant height in some way, so that I will be able to do integration easily. So to do that, you can see here there is a triangle ACD and there is a triangle AOB, right? I can see triangle ACD. In the triangle ACD, angle C is 90 degree, and in triangle AOB, angle O is 90 degree, right? And another thing, if you observe, is this angle and this angle are also going to be the same. So from here, by AA rule, I can say that both the triangles are similar. So triangle ACD is similar to triangle AOB. So I am going to write that here. Triangle ACD is similar to triangle AOB in that case, right? So triangle ACD and triangle AOB are similar. So I can write the ratios like this. So of course AC upon AO is equal to CD upon OB is equal to AD upon AB, right? Okay, what is AC upon AO? AC is Y and AO is H. So Y upon H, Y upon capital H is equal to CD upon OB. What is CD? CD is small r and OB is capital R. So CD is small r and OB is capital R is equal to AD upon AB. What is AD? AD is let's say the length L here, okay? So this length is L, correct? So this length is L, and I'm going to integrate over that. Now I have assumed in general this ring is at distance L. So this is L divided by AB. But what is AB? AB is capital L, right? Okay. So from here I can see this, right? I can write R and Y in terms of L. So I can write R by capital R. So let me use a different color, maybe R by capital R can be written as small l by capital L. So R, small r is L into capital R by L. So here instead of R I can put that value, and again I can write small y as L into capital H by capital L, right? So let's do that here now. Okay, so now I will go change colors. So this will be 2 pi sigma upon M integral R into Y. So R is L, so I can write it as R by capital L into small l, and this can be written as L square H by capital L. So I can write this as 2 pi sigma RH by ml square integral L square dl. Okay, I forgot dl. So this is dl. So now the dl integral, the dl limits will be from 0 to capital L, right? So I will integrate from 0 to capital L. So this is 0 to capital L. So this will be 2 pi sigma RH by ml square, and this integral will be L cube by 3, and the limits are capital L final and 0 initial. So now this will become 2 pi sigma RH by ml square into L cube by 3 minus 0 cube. So I will not write here, but sigma is something that I know already, which is m by pi r L. So sigma can be written as m by pi r L. So this will be 2 pi m by pi r L into ml square into r into h into L cube by 3, right? Correct. So now I can cancel out this pi and pi, this m and m, this r and r can be cancelled out. H is not cancelled. Okay, sorry for that. H is not cancelled. I can cancel out this L square into L is L cube. I can cancel with this one. So eventually you get 2h by 3, right? Now this 2h by 3 is the center of mass of this right circular cone. But here you have to write this center of mass from the apex. But usually they will ask you the center of mass from the ground, okay, or from this point, from the base. So the entire height is h, so the center of mass from the ground or the base will be h minus 2h by 3. So h minus 2h by 3 will be h by 3. So this is the center of mass of a right circular hollow cone from the base, right? Okay.